Yeah, and also if you want, you can actually start the recording yourself. So anyway, so recording is started. Just to let you know that this is being recorded. So then, and then at the end of April 27th, Monday, will be the Chapter 10 mass storage quiz due date. Again, you can take these at any time. You don't have to take them at a specific time, but just before midnight on those particular days. And then on Monday, May 4th, which is the Monday of finals week, the Chapter 12 programming exercise is due, and that is optional. That is 10 extra credit points if you'd like to pick up some extra credit points. And then we'll go ahead and move to Chapter 8, main memory slide. Oops. So I'm in the process of sharing the new slide set. Okay. So can you see the title slide? I'm hoping you can on main memory. And let's go ahead and jump to where we left off. So going back one, we talked about the concept of logical address space and how there's a mapping between the logical address space and the physical address, which is the physical address is the addresses as seen by memory. And then the logical address are the addresses as generated by the CPU, logical or the virtual address. And that will come more into play when we discuss virtual memory. So those are the different components. And so we have hardware to support the mapping of virtual to physical addresses, or logical to the physical addresses is the other way to say that. Many possible methods are possible, and so we will cover that. And then to start with, we consider a simple scheme where the value of the relocation register is added to every address generated by a user or process at the time it is sent to memory. So this is the idea of a base register or a relocation register, which is the beginning of where the current processes code starts. And this was used by MS-DOS. It actually had 4 relocation registers, so it could switch between 4 different registers. And the user program deals with the logical addresses, and it really never sees the real physical addresses, and the execution time binding actually maps it to the physical addresses via the MMU. So please remember that the hardware that does the mapping is called the memory management unit, or the MMU. So dynamic relocation using relocation register is pretty straightforward. The routine is not loaded until it's called, which allows for better memory space utilization. Unused routine is never loaded. And so here we're doing it as we go, in runtime in a dynamic fashion. So all routines are kept on disk in relocatable load format, and then it's loaded in with addresses relative to the relocation or the base address. So no special support from the operating system is required, and it's implemented through program design. The OS can help by providing libraries to implement dynamic loading, and we'll look at dynamic linked libraries later on in this section. So any questions? Pretty straightforward. You just take the base address, relocation address, and we add it, the relocation, to come up with the physical address. So in this example, we have the logical address is 346. The relocation register is 14,000. So we just add 346 to 14,000 to come up with the physical address. So that's how the logical address is mapped to a physical address. Dynamic linking. So here, this is the dynamic linked libraries I was referring to earlier. So system libraries and program code are combined in the loader into a binary program image. And so, so in dynamic link libraries, there's actually linked in a small piece of code called a stub, which is used to locate the appropriate memory resident library routine. So that is what actually exists in the code, is the code to find the library and do the appropriate loading of that library into memory. So the stub replaces itself with the address of the routine and executes the routine once the library has been loaded. And so at that point, all references are directly to the memory instead of going through the stub. Once the dynamic linked library is loaded in memory, it can be called directly. But the first time and before the dynamic link library has been loaded into memory, it actually is a stub that goes through the process of loading the dynamic link library in. So the operating system checks if the routine is in memory. If not, in the address space, they add it to the address space. Dynamic linking is particularly useful for libraries, and so hence in Microsoft Windows we have the dynamically linked libraries. Other operating systems have similar concepts, just slightly different names. The system is also known as shared libraries, and in the case of patching system libraries, where system libraries have been correcting, versioning may be needed. How many of you are familiar with DLL hell, which it was referred to? Has anyone heard of that term? Yeah, so Bailey has heard of it. And so Bailey, what was the issue with DLLs and versions? Oh, she may not have a microphone, so you can chat it as well if you like, Bailey. Okay, so Bailey says she's heard the term, but she's not exactly sure what the issue is. So what the issue was code was written was written and tested using a specific version of the DLL, and then updates to the DLL, either corrections or modifications of technique or whatever, would have a new version of the DLL, and the old code was written and tested using the old DLL. So what would happen is the program would start up and get a new version of the DLL, and all of a sudden the program would stop working. So there became the need to specify what version or versions, multiple, can be used with that particular program, so that you could use the appropriate version of the library that is compatible with the program. So you didn't have to worry about all of a sudden your application would stop running because the wrong version of the DLL was being used and it was incompatible. So that's what the DLL hell was all about. And so that was the solution, is that you were able to specify what versions your application was compatible with. So swapping is the process of swapping processes in and out and their memory in and out. So process can be swapped out temporarily out of memory to a backing store and then brought back into memory for continued execution. So the total physical memory space of a process can exceed the physical memory, and that's because you can swap out a process's memory into a backing store on the disk, and then it can be reloaded back in. So here we have the sum of all the processes running, their memory usage can exceed the physical memory by swapping in and out the processes memory as a context switch happens. So you roll in, you roll out and roll in the various blocks of memory. Swapping, there's various schemes for doing that, of swapping them out, because you probably want to keep in as much of the memory as possible. And so there's ways of deciding which processes memory to swap out. Generally, they can be priority-based schemes in which higher priority processes can be have their memory stay, and then the lower priority ones would be swapped out. Other ways are based on frequency of use and different algorithms like that. The major part of swap time is the transfer time, because it takes a long time to transfer all of the memory, the contents of the memory, out to your backing store and then back in. So that is very expensive, because that is, in general, disk I/O, which is quite slow. So the system maintains a ready queue of ready-to-run processes which have memory images on disk. So there we can see, as part of the PCB, the process control block would be the location of the swapped out memory. Swapping, so the swapped out process needs to swap back into the same physical address. And the answer is, what would you guess? Well, I guess you pretty much know from the bullet point below. It depends on the address binding scheme being used. If you are able to relocate the base or relocation address, then you could swap it back into a different address and everything would be relative. But of course, it depends on the scheme you're using. Certainly, if you're using absolute addressing, which is rare because that is required at compile time, and not since the days of MS-DOS was that used, that you may have problems. Modified versions of swapping are found on many systems, Unix, Linux, Windows. Swapping is normally disabled and started if the threshold of amount of memory allocated is hit. So basically, you've gotten to the point where you're starting to use up all the memory, and then the swapping will be enabled. And it's disabled again once memory demand is reduced below that threshold. So basically, you have enough free memory. So as you look on your PC and you look at some of the performance monitor software, you can see that in fact happen, where you can see the performance will be quite strong until the amount of memory that's being used becomes large compared to the amount of physical memory available, and then all of a sudden performance drags. And part of that is the swapping that is occurring, or can be the swapping that is occurring. So the context switch time includes the swapping. So basically, you have to keep in mind the swapping in and out of memory is now part of the swapping time when you are doing swapping. And so that can drastically increase the context switch time. And so there you can see that you certainly want to reduce the amount of context switches when you get to a situation where the memory is starting to dwindle, the available memory is starting to dwindle. So for 100 megabyte process swapping in and out of the hard disk at a rate of 50 megabytes per second, you can see that the swap out time is 2,000 milliseconds, which is quite large in terms of CPU realm of timing. Total context swapping component time of about 4,000 milliseconds, or 4 seconds. And you can see now we're really starting to pay a penalty. You can reduce it is if the size of the memory swapped is smaller. And so here we start looking at possibilities of only swapping out a portion or portions of a process's memory and leaving as much as we can in. There's other various constraints that are involved. Some is competing pending I/O requests, and being able to make sure that everything ends up in the right address space and the wrong and associate with the right process. And so generally that there's a technique called double buffering, which adds overhead, but allows us to manage the I/O contention that occurs at that point and keeping the process straight. And so that is a technique that's used for in the swapping out of memory. And standard swapping is not used in modern operating systems because there are so many limitations and problems. And so there are lots of modified versions of this concept. So this is primarily a concept that is the basic background of it, but we have more advanced techniques for making this efficient and having this happen. And again, remember that you only do swapping when the amount of free memory is low. So on mobile systems, we're talking like phones and tablets. Typically, swapping is not supported. If it is supported, it's flash memory based, and you're talking about small amounts of space on a flash memory, and there's generally poor throughput between flash memory and the CPU, so it's typically not supported. Instead, other methods are used to free memory if it's low. In iOS, it asks applications to voluntarily relinquish the allocated memory. And then we try to throw out only the read-only data. And in fact, it only throws out the read-only data and not actually the data that is being written to or modified. And then failure to free can result in termination. The iOS does reserve the right to terminate an application. For the Android operating systems, it also terminates if the memory is low, the free memory is low, but it first writes application state to flash for faster restart. But so that's just the state, but not all of the memory. Both OSs support paging, as we'll discuss later. The concept of paging, which is a more advanced technique for a more refined technique for swapping. So the first concept we have here for memory usage is continuous allocation. And that's where the memory for a particular process is all contiguous in one space. And this is the certainly what would be involved with the base address and a relative address to that the relocation address, where everything would have to be contiguous, otherwise it would not work. So the other thing is that the main memory needs to be managed so both the operating system processes and user processes can coexist and use the memory. You could imagine that the operating system processes may take precedence or have higher priority over user processes. So since memory can be a limited resource, we must allocate it efficiently. Continuous allocation is one of the early methods that's used. Main memory is usually divided into two partitions. The resident operating system usually held in low memory with interrupt vector. And then user processes are held in high memory. Each process is contained in a single continuous section of memory. And then we have, like we talked about earlier, the relocation registers used to protect user processes from each other because they are starting all at different locations. And then we have the limit register that specifies the largest address that can be used by that process. And the MMU takes care of this protection and this mapping that happens dynamically. So we have hardware support for it to make this efficient. And then we can allow actions such as kernel code to be transient and kernel changing size as it's mapped in and out. So this is the concept of contiguous allocation. But as I hinted at earlier, other schemes have been developed that are a little bit more refined. So we have one concept, which is multiple partition allocation. So the degree of multi-programming is limited by the number of partitions. So you have hard partitions that are set aside. And so then that is the amount of number of processes that can be managed concurrently is limited by the number of partitions. We have variable partition sizes for efficiencies that they're sized according to the given process needs. So basically the process will advertise how much memory it needs and desires to have. And so you allocate them within the available memory. We can see here, one example is process 5, 8, and 2, and then process 8 completes, which would leave a hole in memory at that particular location. Process 9 comes in and takes a portion of that, leaving a smaller hole, and then process 10 comes in and then leaves yet another smaller hole. So we can see here, I've used the term a hole, which is a block of available memory that exists in memory. And you can see that over time, as processes come in and out, that your holes would be scattered throughout memory. And again, I've already implied this other part about freeing, leaving its space. And so key thing here to remember is that operating system needs to maintain information about the allocated partitions and the free partitions, the whole. So not only does it have to maintain this information, but we'll see that this solution will quickly fall apart if it's not managed. And so that's what we'll head into now. So how do we satisfy a request of size n from a list of free holes? So we may have enough space, but they may be scattered across multiple holes, or there may be multiple holes from which we can choose from that may be big enough, but which one do we choose? So one solution for picking a free hole in order to fulfill the memory request from this process is the first fit. And that's allocate the first hole that's big enough to fit. So we would go marching down or looking down from the bottom part of memory and just go up until we find the first hole that is of sufficient size, and then we put ourselves into that hole. Another algorithm that could be used is best fit, and that is we want to grab the smallest hole that is big enough to handle the request for that process in terms of memory. The advantage of the smallest of the best fit solution is that it leaves the smallest leftover holes in memory, that it allows for the most efficient and leaves the biggest portions of memory available for those processes that need it. And then we actually have a worst fit algorithm, which it seems contrary that why would you pick the worst one? But in this case, we allocated the largest hole. We picked the largest one, and no matter what the process memory needs are, we pick the worst or basically the largest hole, no matter how much we need, which is be the worst fit. First fit and best fit are much better than worst fit in terms of speed and storage utilization. So you could imagine that worst fit would have to be a very special case where you would choose to use worst fit, but in general, first fit or best fit would be the solution that is taking it back. And please remember that the best fit algorithm, as kind of described in the name, result in the smallest leftover holes in memory. So with this scheme, we have a situation with fragmentation. You've probably heard of fragmentation in terms of disks, and it's a very similar problem that you have in disk. And so we have two categories of fragmentation. External fragmentation is when the total memory space exists to satisfy a request, but it's not contiguous. So this is external, means all of the process as a whole, because of the non-contiguous nature of the allocation of the various memory as processes get swapped in and out, you have fragmentation on an external level. Internal fragmentation means that we've grabbed a block of memory, but the amount of memory that is actually given to the process may be different than what is actually given to the process. And that's because generally there will be a block size to help in the management of the process. If you had completely variable length blocks that you allocate, the management problems becomes very, very difficult. So in general, we allocate fixed size number of blocks. So you could have a process come in with 3, 4, or 5 blocks, but the or request or get, like 5 blocks, but it may only be using 4.5 of them. The last block is not fully being utilized by that process, and that would be the internal fragmentation. So first fit analysis reveals that given n blocks allocated, half of the blocks are lost to fragmentation, and so which is basically a third may be unusable, which this is the 50% rule, and that's sort of a guidance factor for the first fit algorithms, is that when you're using a third of your memory, that only, is that right? I think it's backwards. When you're using half of your memory, only a third of it's usable at that point. So one technique, and I'm sure you've seen this with defragmenters with hard disk, is we can use compaction to reduce the external fragmentation. That is the fragmentation of all the processes' use of memory as a whole. And basically you're shuffling memory to place them in contiguous blocks again and gather up large blocks of free memory. Compaction is only possible if relocation is dynamic and is done at execution time. Otherwise, this scheme won't work. And again, we have the complexities of managing the I/O in and out. And then we can also see that the backing store, or basically the storage space on the disk, also has the fragmentation issues of the disk. So some additional fragmentation issues is actually the swapping out to disk and the fragmentation that may will happen on the disk as well. So another scheme is segmentation, and that is supporting the user's view of memory. And this supports a segment because we know that that we are looking at. Sorry, I'm starting to multitask here. Segments of main program, the procedures, functions, methods, objects. We have the stack, the heap, local variables, global variables, which global variables would be your heap, and then the stack, and the symbol tables and arrays. And this logical address scheme is what we are used to seeing from a programmer's point of view. And so one technique that is used is to try to model this based on based on the users, how the user views memory. And so what we look at here is this segmentation architecture. And so with the segmentation architecture, the logical address consists of a tuple. It's the segment name. It says segment number, but technically you can think of it as the segment name, which is the namespace, like main user program, the heap, the stack. Those would be the names. Then for the efficiency of implementation, those names are then mapped or given numbers. So we then have the tuple segment number and offset, but keep in mind that this comes from the named, basically the user named addressed segments, and that gets mapped to a number, and then you have that offset into that memory segment. So again, this is trying to take advantage of what the user modeling after what the user is doing in terms of the user applications codes use of memory, and trying to map it to that to most closely model what the user is trying to do. So here we have a segment table with the segment number offset, and those would need to get mapped to a physical address, which is the base address, and the limit, which is the length of the segment. The segment table base register points to the segment table's location in memory. So there's actually a table that contains the segments. So you can see here, this table would have the information about segment 1, 4, 2, and 3 in this diagram on the left. And the segment table length register indicates the number of segments used by the program. Protection: with each entry in the segment table, a valid bit means that it is a 1 means that it's a valid bit, which is it is valid for this particular process, that it is in memory, and 0 means that it's a legal segment. This is somebody else's memory. So here is the protection mechanism to keep processes from stepping over each other's memory. Is this protection mechanism or information that's recorded in the segment table. The protection bits are associated with the segments, like I said, and code sharing occurs at the segment level. So again, you could have other processes go in here and record where their segments are. Since segments vary in length, memory allocation is a dynamic storage allocation problem. So not only are you managing memory, but you also managing the segment blocks in terms of some unit of storage. So here we have a pictorial diagram of what a segmentation MMU or segmentation hardware would look like. The CPU has the segment number at this point and their offset, and we look at putting in their segment table the segment which has the base and the limit, and then we have the offset, and then we check to see if with that offset, is it less than our limit? In fact, or are we exceeded our segment? If we exceeded the segment, we have made an error and we're stomping on somebody else's memory. If not, then we add it to the base and that maps us to segment hardware, to the physical address, sorry. And again, this is basically a specific implementation of the MMU. So next we will be covering paging, but we are pretty much at the end of our time here in class. Does anyone have any questions about what I covered or anything about the class in general? Okay, so probably a lot to take in. I know we went through fairly quick. There's a lot of material with this and the next chapter, which is virtual memory. So again, this is all memory management stuff. But I think this first part was pretty straightforward, but then we'll start getting into some, and then we'll get to some additional refinements. But again, the first refinement that we had was segmentation, a segmentation architecture, and then we'll looking at paging techniques and other techniques that can be used. So with that, unless anyone has any questions, you're dismissed. And I'll go ahead and stop the recording here.